Hello, my name's Jeff Messier. I'm a professor of electrical and computer engineering in the Schulich School of Engineering, and this is Module 14, where we discuss the state probabilities of Markov chains. Okay, just to start off with the definition, a state probability is basically just the probability of being in a certain state at a certain time step. And the notation we're going to use is to represent state probabilities, or the symbol we're going to use to represent state probabilities is pi. So pi I as a function of n is just the probability that the Markov chain is in state I at time step n. And we often group these state probabilities into a vector, which is boldface pi, also a function of n, and it just contains the probability that we're in the first state at time step n, the second state, the third state, and so on. All of these states form a universal set, right? We have to be in at least one of the states at a particular time step. And so when we add all of these probabilities in the vector together, that sum must be equal to 1. And as I'm going to show you on the next slide, we can figure out the state probability vector for any time step as long as we're given the probability matrix P and, this should be a boldface pi, and the state probability vector for time step 0, or basically, in other words, our initial state vector. So the best way to illustrate this is using a simple example. So here we have a binary Markov chain where we've got all possible transitions labeled here. And we want to determine the state probability vector at time step 1, given that we know the probability matrix P and the probability state vector for time step 0. So this is the probability of being in each state right at the very beginning of the process. And so what we're going to do is we are going to just take the state probability vector and multiply it by the probability matrix. So let's take a look at our first term. If this works, the first term should be equal to pi 1 at time step 1. So in other words, the probability that we are in state 1 after a single time step. And this makes sense if we look at the two terms making up this the first element in this vector. So the first term is pi 1 of 0, which is the probability that we start out in state 1, multiplied by p11. So in other words, it's the probability that we start out in state 1 and we follow the loopback probability. The second term is the probability that we start out in state 2 at time step 0 and then follow the transition from state 2 to state 1. So the probability that we're in state 1 after the first time step is the probability that we started out there and we loop back, plus the probability that we started out in state 2 and made the transition over. Okay, so hopefully that makes sense. And then the second element in this vector should be equal to pi 2 of 1. And so if we look at the two terms in the summation making up the second element in the vector, we have the probability that we started out in state 2 at the first time step, multiplied by the loopback probability, p22, plus the probability that we started out in state 1, multiplied by the probability that we take the transition over from 1 to 2. And that also makes sense. So the probability that we're in the second state after the first time step is the probability we started out there and stayed there, plus the probability that we were in state 1 and then we made the transition over to state 2. So by induction, we can show that the state probability vector at time step n is equal to the state probability vector at time step n minus 1 multiplied by the the probability matrix. So every time we multiply the state vector by the probability matrix, it advances one time step. Another thing that we can write is that the probability state vector at time n is equal to our initial state vector probability, or state probability vector, multiplied by p to the n, right? Which is basically just another way of expressing this equation. Now, this should hopefully make sense because we know that the probability matrix raised to the exponent of n gives us the n-step probabilities for moving between different states. So if we have the probabilities of moving between different states in n time steps, and we multiply that by the vector containing the probabilities of where we are in our initial conditions at time step 0, then we should get the probability of being in the different, or in each of the states after n time steps. And just as an example to sort of show how this works maybe a little bit more, if we consider our Vocoder Markov chain, let's assume that we have an initial state probability vector that looks like this. So essentially we're saying that when our Markov process starts off at time 0, it always starts off in the lowest rate state, in the 1/8 rate state. After one time step, we can determine the probabilities of being in each state by multiplying pi0 by the probability matrix, and we get this vector, which it's easy to, if you look back at the at our diagram for our Markov chain, state 1 had a loopback probability of 0.8. So the probability that we're still in state 1 after a single time step is the probability that we followed the loopback path, right? So that's why the first term in our state vector is equal to 0.8. And then we made a transition to state 2 with a probability of 0.2, and that's why this second term is equal to 0.2. If we want to determine our state probability vector after 2 time steps, we multiply pi1 by the probability matrix P, and as you can see, we start to spread out a little bit more. We're still most likely to be in the first, to have remained in the first state. We're actually a little less likely to be in the second state because now there's also a chance that we may have gone on to the third state. So you can see how, as the Markov chain, or as the Markov process progresses, we're still influenced by the fact that we started out in state 1, but we're starting to spread out a little bit to the other states. And note, like we said in the previous slide, if you want to just check your calculations to make sure that they're correct, the probabilities in these state vectors should always add up to 1. So in the last example, we clearly saw the influence of the initial state vector, right? We set the initial state vector to always start in state 1, and that clearly influenced the state vectors in the subsequent time steps. But we saw that, after a while, even though state 1 was still the most likely, the probabilities started to spread across the other states. So it's reasonable to think that after a very large number of time steps, or perhaps an infinite number of time steps, that the influence of the initial state vector will basically disappear. And this then would allow us to think, well, maybe we converge after a large number of time steps to perhaps a state vector that's constant. And for many Markov chains, this ends up being the case, and we call the state probabilities after a large number of time steps the limiting state probabilities. And so we can kind of illustrate this by extending the Vocoder example. So here I've got 3 state vectors. This is the state vector after 10 time steps. We can see that State 1 is still the most likely state, so we still see some influence of the initial state vector, but we're starting to spread across to the other states, certainly. After 50 time steps, we see that things are starting to spread out even more, and in fact, the probability of being in state 1 and the probability of being in state 4 are almost equal, even though state 1 is still a little bit higher. After 100 time steps, we can see we're starting to converge, right? So the probabilities for state 1 and state 4 are equal to the number of significant figures that I'm showing in this slide, and we no longer see any influence from the initial state vector at all. And so to formalize this idea, the limiting state probabilities of a Markov chain are basically the state probabilities after an infinite number of time steps. And we represent these limiting state probability vectors just by the vector pi, where we're no longer showing pi as a function of n, because we assume that we've gone essentially an infinite number of time steps. And so the limiting state probability, the individual limiting state probabilities for each state are just pi 1, pi 2, and so on. If the limiting state probabilities exist, and they don't always, but if they exist, then we say the Markov chain is a steady state or has a steady state. We say it's a stationary Markov chain, or we say that it's time invariant. And the limiting state probabilities always exist if the Markov chain is finite, which is basically always the case as far as our class is concerned, irreducible and aperiodic. If it's not irreducible and not aperiodic, then there's still a chance that the limiting state probabilities might exist, but it's no longer guaranteed. Another useful property of the limiting state probabilities is that it can be shown that the limiting state probability for state j is equal to 1 over the mean time of recurrence, what's known as the mean time of recurrence. And the mean time of recurrence is the expected value of tjj, and it's basically the average number of time steps it takes to return to state j. So once you leave state j, the mean time of recurrence is the average number of time steps it takes to come back. So if state j is recurrent, the limiting state probabilities are equal to 1 over the mean time of recurrence. If a state is transient, then the limiting state probabilities are always equal to 0. And so that means that after an infinite number of time steps, the probability of being in a transient state is 0. Remember, transient states are ones where there's a possibility that we can leave them and we never come back. And we assume that after an infinite number of time steps, we've basically tried all possible transitions in the Markov chain. So if a state is transient, we would at some point have taken the path of no return out of that transient state, and the probability of being in the transient state after an infinite number of time steps is equal to 0. We can also say that if pi j is equal to 0, then the mean time of recurrence is 1 over 0 or infinity. So it means that, again, for transient states, once we leave that state, the average time that it takes to come back is basically infinite, or in other words, we never return to it. Now I'm going to show you a couple different techniques to solve for the limiting state probabilities. The first technique is to take the probability matrix n and raise it to a very, very large exponent. In theory, infinity, but if you're working in MATLAB, you can raise it to 1,000 or 2,000 or something like that. And if you do that, you'll find, if the limiting state probabilities exist, that the columns in the, and we'll call PSS the steady state probability matrix. The columns in the steady state probability matrix are the same, and they are equal to the limiting state probabilities. So the first column will be equal to the limiting state probability for for state 0. The second column will be equal to the limiting state probability for state 1, and so on. So why does this have to be true? Well, we know that the limiting state, we know that the probability, or the state probability vector at time n is equal to our initial state, our initial state probability vector multiplied by the probability matrix to the n. And so our limiting state probability vector has to be equal to the initial state raised to the infinite exponent, or in other words, the steady state probability vector, which is, or the steady state probability matrix, which is what I'm showing here. So the only way that this can, so basically what this means is that regardless of the content of pi 0, we always have to come up with the limiting state probabilities. Now, the only way that this is possible is for the column in, or the columns in each of the, or the only way that this is possible is for each of the columns in PSS to be equal to the limiting state probability. Because, and I'll illustrate this in the next slide with a smaller example. So let's consider a 3-state Markov chain where we have a certain initial state vector, and our steady state probability matrix has 3 columns, and each column is equal to the limiting state probabilities. We argued on the last slide that the limiting state probability vector is equal to the initial state vector multiplied by the steady state probability matrix. Now, this initial state vector can be anything, right? The limiting state probability vectors need to be independent of the choice that we make for our initial state. The only thing that always has to be true for the initial state vector is that these initial state probabilities have to sum to 1. Okay? So when we multiply our initial state vector by our steady state probability matrix, we have a single row, and we just do row column multiplications like we always do with a matrix. And so that means to determine the first value in our limiting state probability vector, we take the first column and we multiply it by the row of the initial state vector. And if each one of these elements in the first column is equal to pi 1, we basically have pi 1 multiplied by the sum of the initial state vector. Now, these values in the initial state vectors can be anything, but they always have to add up to 1. So regardless of what we choose for the values in our initial state vector, this first element is always going to be equal to pi 1. And I shouldn't have shown dots here because the result of this multiplication is a vector. So it's going to be a 3-element vector where the first element is equal to pi 1, the second is equal to pi 2, and the third is equal to pi 3. So we've seen that one way to determine the limiting state probabilities is to just take our probability matrix and raise it to a large exponent. And that's a good method, particularly if you have access to MATLAB or some kind of scientific computing package. But depending on the size of your Markov chain, it might be a little cumbersome. So there is a second way, and you can find the limiting state probabilities just by solving a system of linear equations. So the system of linear equations can be found by making 2 observations. The first one is that if we multiply the limiting state probability vector by the probability matrix, then we should still get the limiting state probability vector. So why does this make sense? Well, remember that the limiting state probability vector represents our state vector at an infinite number of time steps, right? So if we take our vector and we multiply it by p, we get our state vector at basically infinity plus 1 time steps, but that shouldn't change the vector at all, right? So that observation allows us to write this first equation. The second observation is that our limiting state probabilities always have to add up to 1. So using these two observations, and I'm going to show you an example of this on the next few slides, we can develop a series of linear equations that can be solved using something called a pseudo-inverse. Okay, so let's use this method then to solve for the limiting state probabilities of our Vocoder Markov chain. So the first thing we said was the limiting state probability matrix, the limiting state probability vector is equal to the limiting state probability vector multiplied by our probability matrix P. Okay, so, and then the second observation was that all of our limiting state probabilities have to add up to 1. So if you expand out the, this first matrix equation and you manipulate it a little bit and you combine it with the second summation equal to 1, you get a system of linear equations that looks like this. Okay, and again, the system of linear equations we have on the bottom of the slide here is just a manipulation of this first matrix equation, and then we essentially tack this second summation equal to 1 on the bottom. Okay, so what we're going to do is we have 5 equations, 4 unknowns, and we're going to solve for the 4 unknowns. When you have more equations than unknowns, you have an overdetermined system, and the easiest thing, or what I usually do when I have an overdetermined system, is I solve for my unknowns using something called a pseudo-inverse. The other way you can do this is you can use Gauss-Jordan elimination to reduce the redundant equation and then come up with 4 equations, but I just find the pseudo-inverse is a little bit easier. So in the following slide, let's denote this vector here as y. And, sorry, this is getting a little bit messy. This matrix here as A. The pseudo-inverse then is just this equation. So you're taking the transpose of A, multiplying it by A, taking the inverse of that, and so on. This is something that you can solve in MATLAB. And if you do this in MATLAB, this ends up being the limiting state probability vector. And we can see that this limiting state probability vector is basically equal to the state probability vector that we had after 1,000 time steps that we showed a number of slides ago. So this is one way to check our work. And we also can see, we can also calculate the mean time for recurrence by taking the inverse of these probabilities. So the probability, or the average time it takes to get back to the first and the last state after leaving it is 2.8 time steps, and the average time it takes to return to the intermediate states after leaving them is 7 time steps. Something I should point out as well is, like when we write the limiting state probability equation, where we have the row vector pi is equal to the row vector pi multiplied by the matrix P. This is actually a left eigenvector equation, right? Where the row vector pi's would be the left eigenvector. Normally, I mean, if you're familiar, or the first time you learn eigenvectors, the eigenvectors are columns, and they're on the right-hand side of the matrix. That's what's known as a right eigenvector. If they're row vectors and they're on the left, then they're left eigenvectors. And so pi would be the left eigenvector, and then the eigenvalue would just be equal to 1, the scalar value of 1. Now, in order for this equation to exist, p has to have at least one eigenvalue equal to 1, obviously for this equation to hold. But if it has more than one eigenvalue that's equal to 1, then that means this equation has multiple solutions and there's not a unique limiting state probability vector. And actually it can be proven that in this case, if you try to take the pseudo inverse, it won't actually exist. So a nice sort of way to check whether, or another nice way to check whether the limiting state probabilities exist is to just determine the eigenvalues of p and make sure that there's only one and only one eigenvalue that's equal to 1. So in the vocoder example, you'll notice that that limiting state probabilities existed for all of the states. The vocoder is an irreducible Markov chain that consists of a single class where all the states communicate. So we would expect that limiting state probabilities would exist for all of them. However, this final example is a Markov chain that we've seen before, where just by inspection we can tell that we've got two classes, a class that consists of states 1 and 2, and another class that consists of state 3. The states in our first class, states 1 and 2, are recurrent because this class is a closed class. However, state 3 is transient. It's an open class, and it's transient because if we take the transition from state 3 to state 1, we'll never ever return to state 3. And so using any of the techniques, and I would encourage you to do this just for practice, use all the techniques that or I guess both of the techniques that I presented in the last few slides to solve for the limiting state probabilities. And when you do that, you'll find that the limiting state probabilities for the three states are 0.5, 0.5, and 0. We knew that the limiting state probability for state 3 had to be 0 without doing any calculation at all because it's a transient state. And this is the nice thing about having the ability to look at a Markov chain and to see which states are transient, which states are recurrent, because it does allow you to sort of check your work a little bit when you're calculating the limiting state probabilities. And so this means that the average time to return to state 1 after leaving it is equal to the average time it takes to return to state 2 after leaving it, which is 2 time steps. And of course, the mean time for recurrence for the third state is infinity.